welcome everyone. The last Alaska Tech Talk of 2025. It's nice to see everyone. It's our Tech Talk number 31 already. And first of all, please note that this session is being recorded since we will be uploading this to YouTube later on. The Alaska Tech Talks, for those who have maybe never been here before, is a format that is hosted by the Alaska Association. Alaska is on a mission to strengthen digital sovereignty in Europe, and we do this by developing open source technologies that help to build and run cloud infrastructures, sovereign cloud infrastructures. And we also believe that sharing knowledge and exchanging ideas is very crucial too. So this is why we have established this format where we come together once a month to talk about just new technologies, fresh ideas, and have some discussions. My name is Ariane. I am moderating this session today, and we will hop right into the agenda. Nothing new, same as always. The Tech Talk, the actual Tech Talk will start in a second. Then we have some time to speak about some news and events where you are all always invited to also share if you have something from your side that could be interesting for the community. And then we will look at the next Tech Talk and look at what's expecting us in 2026. So it is my pleasure to welcome Martin Morgenstern from Cloud and Heat Technologies. He's a DevOps engineer, and he will be talking about in the Airflow, OVN and OpenStack. And honestly, this is all that I have to say. I will hand you the mic or give the stage to you, Martin. Stop my screen sharing.
Thank you very much. So it seems like you can already see my slide. Welcome everybody. It's an honor for me to speak here today. I'm a bit nervous, but I think we'll get it going. So the topic today will be OVN and OpenStack in the Airflow. We will discover later what that means. I myself working daily with OVN and OpenStack, and I think I can share a thing or two about that. The intended audience for this talk is I cannot change the slides. Oh no, I'm not the presenter. Maybe now. So fixed. The intended audience for this talk is ideally you're an OpenStack user, maybe a power user, and you already created some neutral networks and subnets and ports and so on, ideally on the command line, because there you see what you actually need to create manually. And on the other hand, you didn't bother yet, or maybe you didn't have time to look under the hood and see how the things are actually implemented in OVN. And my goal for you would be to understand the architecture. So we'll cover a lot of the architecture today. You understand how the logical elements are mapped down to the physical layers. You will get a glimpse on how the packets flow. And ideally, at the end, you have an idea when things don't work anymore, that you know where to look, right? So there are so many places where things can go wrong, and especially if you're just a user, it's hard to grasp where you could look for. Yeah? Maybe if you want to do a TCP dump, you have to know where to look, which interface, and so on. And I brought some nice little graphs with me to show how that works. Yeah, and maybe you know the Horizon UI of OpenStack. So if you created something like that before, you're right here. So this is a typical topology that you can create with OpenStack. And yeah, we will go from here. So let's dive right in on what is OVN and how does it relate to Open vSwitch. So first of all, it's production ready virtual networking solutions. It's for virtual machines, but also for containers. So it's the primary choice for OpenStack networking, of course, but you can also use it in Kubernetes if you want. So there's a OVN Kubernetes CNI provider. And it's based up on Open vSwitch, which provides the low-level plumbing, so to say. And that's a virtual switch, which is implemented in C. and it of course runs on Linux, but you can also run it on FreeBSD, NetBSD if you want. You program this virtual switch with OpenFlow. It brings a set of daemons, for instance, the Open vSwitch or OVS vSwitch daemon and the kernel module. So the flow-based switching is implemented there at the kernel level. It's called the data path, kernel data path. And there's also a database daemon, OVSDB, which is used to store the configuration. And that stuff is also used in OVN. I will come to that later. OVSDB can be run with different schemas, which are defined in JSON in a very simple way. And the wire protocol that they use for OVSDB, so if you want to connect to an OVSDB and get the data, is based on JSON RPC. And now let's come to OVN, which stands for Open Virtual Network. This is the thing that provides the high-level abstraction to define your network topologies. So things like layer 2 and layer 3, like routers and a network and so on. And it's also written in C, so mainly platform independent. It runs completely in user space, so you don't need a kernel module for that. But of course, if you base this whole stuff on Open vSwitch, you need the Open vSwitch kernel module. So at the moment, that's the way to go, but there is also experimental support for user space, data path drivers, most prominently DPDK, if you maybe know that. And OVN then provides virtual routers, switches, access controllers, and so on, and all that also in a distributed fashion. And it also provides some more daemons, which are responsible to translate the configuration of OVN, which we will cover in a minute, into the actual networking setup down in the physical layers with OpenFlow. It reuses OVSDB and just runs this with different schemas. And all of that is completely free and open source and Apache 2 licensed. And by the way, that are the logos of the projects. Yeah. So let's dive right into the layered architecture of OVN. Maybe you have seen this. There's a really cool man page that you can check out, which I recommend to you if you want to dig even deeper. But the most important thing is that the stuff is layered in layers. And at the top, you have got a cloud management system. In our case, it's OpenStack with the OVN plugin. And the CMS is supposed to talk to OVN via the northbound database, which is an OVSDB with a special schema. There are all the high-level entities, such as a network, a router, and so on. They are all saved in this database. Then you have a daemon, which is called the OVN northd, which translates this into logical flows, which are residing in the southbound DB. And then at the lowest level, you have got hypervisors, for example. So I took this directly from the OVN architecture page. Let's say you have a few hypervisors, and on them you need to run an OVN controller. You need to run the OVS vSwitch daemon and an OVSDB server locally, which is responsible for storing the configuration of the local virtual switch. And to get a little bit more detailed here, so to see what's at each layer. So let's start at the top. If we go to the CMS, in our case OpenStack, you have the entities that you already know, like a router, network, subnets, and so on, security groups. And the communication happens, as I mentioned, via JSON RPC. In the northbound database, you have different entities, different schema, which is called the OVN northbound schema. There you have entities like NB Global, which is basically just a singleton entity used to store some configuration data, maybe a thing like a revision of the configuration that's currently running and which is currently running down in the physical layers, so that OpenStack knows if everything that it requested from OVN has materialized at the lower layers. But you've also got all the corresponding things like a logical switch, which corresponds to the network, logical routers, the ports, logical switch ports, ACLs, and so on. And this in turn is taken by the OVN Northby, which translates them into logical flows. And it does this via incremental processing, which is very important, especially if you have a big environment with a lot of hypervisors, a lot of nodes. Then an update which computes everything will take a long time. And so they optimize this and have an incremental processing engine which just recomputes things on demand, only the things that changed, and which is really, really important to keep the reconciliation times low. Then the next layer would be the southbound database, basically again an OVSDB with the OVN southbound schema. There you find entities like SB Global, which is again a singleton entity storing some global configuration data. You have information about the chassis and some optimized version of it, which is called chassis private. You've got the logical flows, which were created and populated by the Northby. They are now saved in the southbound DB. But you also got things like a port binding and so on, which basically says at which chassis, which I come to in a minute, is some port residing. The term chassis is what I put here. So if you take these boxes here, in my case, they are hypervisors, but if you're a network person, the terminology for that is usually the chassis, and also the OVN folks say chassis to that, and you have this term all around. So from now on, I will usually say that this is a chassis, and this is also a chassis, and on each chassis, you need to run an OVN controller and the accompanying daemon and database, right? And let's go to the chassis. What's happening there? You need an OVN controller. This is like a little agent which translates the logical flows into the actual physical flows, which are represented by open flows. And again, we have incremental processing here as an optimization. And then down below, you've got the OVSDB server, which is just running the Open vSwitch database schema, which is configuring the OVS vSwitch-D. So you have like the entities, Open vSwitch, you have switches, ports, and data paths, and so on. Yeah. Good to know here is this JSON RPC wire protocol that they are using is specified in an RFC, which is called the Open vSwitch Database Management Protocol. And also good to know, all of this is using a monitor approach or a push-based mechanism. And basically what you do, for instance, if you're a client like the OVN controller and want to connect to the southbound, you can just say to the southbound DB, please monitor some of the tables for me, maybe the chassis table or something like that, and notify me when things change. And this is instead of a pull approach, you get notified when things change. And also each client of an OVSDB will replicate the subset of the data and update this subset of the data when it gets notified by the server. And now an even more detailed example. So this is the basic architecture with all the details, what happens at each layer. But usually you want to go a little bit further and want things set up in a highly available fashion. And this you can do with Open Virtual Network. So the OVSDBs support running in different modes, which I mode before was just the standalone mode, just running one instance of the OVSDB, but you can also run it as a raft cluster. And I've shown this here. So I replaced the single northbound DB with a cluster of 3 nodes. And then you have, like it's typical in a raft cluster, you have a leader and a follower set up. And if one of them goes down, you can tolerate that and you can continue processing, maybe if you're doing a node maintenance or if there's an outage, etc., etc. The same can be done with the southbound because it's also just a normal OVSDB. The northd can also be run in a cluster fashion, but it's not a raft cluster. It's just an active and hot standby mode, which you can use. And there is like a mechanism that ensures that only one of the OVN northds is active by acquiring a lock. And one more important thing is if you have a big cluster with a lot of chassis, you usually do not connect your chassis directly to the southbound, but you put relays between southbound and the chassis and the OVN controllers. This is just another mode how you can run an OVSDB, which is called the relay mode. What I also introduced here is another term. What you often do in big environments, that you have separate node roles. So for instance, you already know the hypervisors where your workload, where the customer workload is running virtual machines. And then you have dedicated networking nodes, which we call gateway nodes usually. And this is just here to show that the setup can look like this. And on a gateway node, you also need all this stuff that you need on a normal chassis, so OVN controller and etc. Now let's have a look at the terminology planes, control plane and data plane, which is a little bit difficult, in my opinion, to describe here. So what defines the data plane and what defines the control plane in this case? So the upper part here is definitely control plane. If you have an outage here, then the workload and the networking can still run. But there are some caveats. For instance, you shouldn't live migrate a virtual machine, or you cannot do any changes to the networking, but everything which is already there basically works. As long as your data plane is still running. So if something of this here is crashing or like killed by someone by accident, then you will have a data plane outage and your customers will notice. But it's difficult, like I've said, because there are cases when the OVN controller is not running, that you can also have an outage, because sometimes the OVS vSwitch daemon needs to do an upcall. This is hard to see in this slide, unfortunately, but here you can see it. It needs to do an upcall and ask the OVN controller how it needs to perform specific things. And if the OVN controller isn't there, of course, then this action cannot continue, and then maybe packets need to be dropped, and your workload will notice this, right? Okay. Then next, I always find it very interesting and also really important to have a look at the from a logical point of view, how the networking look like, how the customer networks or the tenant networks are separated. And there you hear often the terminology overlay and underlay network. And I just brought a slide to explain how that works. So in OVN, the choice to provide the overlay network is Geneve. And it's just a protocol that encapsulates the tenant networks. And in our underlay network, I've just brought a very simple topology. I brought again some gateway nodes and a few hypervisors. And the layout is not by coincidence. So everything which is like on this line here runs on the gateway 1, everything on this line runs on gateway 2, and so on. And yeah, the basic thing that you need to take into account is like the underlay network is that what's there physical, and the overlay network is basically that what is entirely virtual, which is provided in the OVN case by Geneve. And each tenant network gets a separate VNI, which is the virtual network identifier. This is just a 24-bit identifier that is used for distinguishing to which project, to which not project, to which network, virtual network, a packet belongs. And in this case, we have two of them. Let's say we have a look at the blue one. The customer here is running two VMs. The one is on hypervisor 1, the other on 3. And he also created a virtual router. Everything is connected in a tenant network here. So the router and the two VMs are inside one network. But we also have a gateway port, which is connected to the provider network. And it also has a floating IP attached. And now let's see how we can talk to the outside world from a VM. So how would the traffic flow in this case? So this is this line. Basically, if you look at the physical layer, if the VM4 wants to communicate with some entity outside on the provider network, it would go this path. So when it leaves the hypervisor, it will be encapsulated in a Geneve packet, and it will get VNI. And then it will travel to the gateway node where the virtual router is just residing. So in OVN, this can be done in a high available fashion. So if you have multiple gateways, you can assign a virtual router to all of them and give them priorities. And if some of the gateway fails, it will automatically switch them over. And at one moment in time, of course, only one of the gateway is the active gateway for a virtual router. And in this case here, it's gateway 2. And because of this, the traffic passes through the gateway. It will again be decapsulated. So basically the Geneve packet will be extracted, and then the packet will be sent to the uplink interface, which is connected to the provider network. And I think this is good to know to put the things in perspective. Let's take a deeper look at gateway 2 and hypervisor 3. So how does this work under the hood? So what makes a gateway chassis? It's just a chassis which has some special options in the OVN configurations. So first of all, you need to pass this option here, enable chassis as gateway in the local Open vSwitch database. You need a bridge mapping, which is there to connect a neutron network to a physical network, which is again mapped to a bridge, which is residing on that host or on that chassis. So in this case, I created a neutron network, which is just called my provider network. And the important thing here to note is that I give this option here, provide a physical network, which just specifies an arbitrary name that I can choose, physnet1, but it has to match the name in the OVN bridge mapping. So then Neutron will basically take that, and it knows that this network here, which is external, maps to this bridge. And on the hypervisor, basically, you need some setup, which you need to do on your own. Or if you're using a solution like Yaook will do this for you. You will need to set up all these bridges yourself and link the ports together and so on. But when it's done, it looks like this. On the gateway 2, you have the BRX, which is the bridge created with Open vSwitch, which is connected to an uplink interface. In this case, it's EDH1, and this is just patched into the provider network. Then there's an integration bridge, and all of this is also patched together on a gateway node. And from this integration bridge, all the tunnels will be created. So you have for each hypervisor, for each gateway, or in general for each chassis pair, you will have a connection, you will have a tunnel, and each of them has a port on the integration bridge. So in this example, you just have one, and the tunneled traffic, so the encapsulated traffic, will travel over the underlay network. So if you remember the colors, it's the same green color that we had on this slide here. It's just the physical underlay network, right? And let's assume the traffic travels back, maybe an HTTP request, and it's responded. It will travel like this way. It will get unpacked here in this bridge, which is provided by vSwitch, and it will get forwarded to the port where the VM is attached to. You might know that it's always called like a tab interface, like this one here. And in the end, it will reach the VM and at the interface that the VM sees. And all of the hard work is happening in this integration bridge, where the name bridge is actually a little bit misleading. It's not just layer 2 functionality, but it also does more, because all the open flows that are generated can do a lot more. OVN will also generate flows that emulate layer 3 functionality like routing, DHCP, and so on. Yep. And another word which is important to know, and which I found quite interesting when I first dealt with OVN and Genève. So let's say you have 4 chassis, then you can have up to 6 of these tunnels, because each pair needs to be connected. So for instance, if a tenant network will span these 2 hypervisors, because there are 2 VMs, the one is residing on hypervisor 1 and the other on 2, then they need to communicate. And then OVN knows, okay, I need to set up a tunnel between these 2 hypervisors. And you will see that in the configuration that is being done by OVN. And in total, this is like the summation formula that you can use for that to compute this. So you can imagine if you have a very big cluster that you have a lot of UDP connections, so to say, a lot of Genève tunnels, which can, by the way, lead to problems with connection tracking. So in some cases, it might need to be required to disable connection traffic just for Genève UDP tunnels, because the table can overflow. There's an optimization. So some of the tunnels are created on demand, especially between the hypervisors, but in practice, you won't notice this, because your VMs are distributed in such a fashion that you will see this full mesh like it's shown here. So now let's talk a little bit about the integration with OpenStack. So in OpenStack, it's done with a new framework that they introduced some time ago to support different backends, which is called the module layer 2. And basically, that's the entry point. You will need to set this as the default core plugin. And it comes with 2 types of drivers, which are called the type and mechanism drivers. And the separation makes it possible to do a lot of reuse. For instance, if you have the type drivers like flat or VLAN, Genève, and so on, you can reuse them with different mechanism drivers, and you do not have to write them again for each of the mechanism drivers, right? And the bold ones here, I just marked them. These are the ones that Yaook supports, because I also wanted to share some things about Yaook and how Yaook integrates with OVN later. The mechanism drivers that you can use with ML2, they are not only OVN, but you can also use OVS and Linux Bridge and so on. and it's even more modularized with so-called service plugins, which you need to set in the case of OVN to OVN router. And in Yaook, we will use the OVN plugin exclusively, or it's being used exclusively. So if you're looking to deploy some old stuff like OVS, yeah, you need to go to a very, very old Yaook release. Yeah, and that's how it's integrated into OpenStack. Now let's have a look at how it's done with Yaook. Yaook uses an operator-based approach because it's OpenStack distribution based on Kubernetes. And there all the stuff begins with the custom resource neutron deployment, which I marked orange here. And then we have different operators which are responsible to turn resources of one kind into one or more resources of another kind. And in this case, we have the neutron operator, which sees this neutron deployment resource and creates some sub-resources out of that. So for instance, for a neutron API, you will need a MySQL server, but you also need a RabbitMQ and so on. This is also represented by some custom resources in Yaook, which are in turn read by another operator, which creates native Kubernetes resources. For instance, for the MySQL service resource, you will get a stateful set, you will get services, certificates, and so on and so on. The details don't matter. It's just important to understand that there's this little graph and that there are different operators, which I marked green here, which are responsible for turning these resources into other resources. And then at the lowest level, you have native Kubernetes resources like a stateful set, deployment, and so on. And in case of OVN, the most important resource is the neutron OVN agent resource, which is created by the neutron operator. It will create neutron OVN agent resources for every chassis. And this is done by labeling your Kubernetes nodes in a special way. If you remember, we had the terminology of a gateway node. The corresponding node label that you need to use in this case is this one, network.yaook cloud neutron OVN agent true. And then it will regard this node as a gateway node and will create an OVN agent resource for that. And in turn, the neutron OVN operator will see this and materialize all of this into native resources. For instance, it will create a stateful set for the OVN controller, but it will also create a stateful set for vSwitch and so on. We'll have a look at that in a minute. But you not only need the gateway node, but you also need the agents on the compute nodes because you want to connect the virtual machines, right? And therefore, the neutron operator also creates neutron OVN agent resources for compute nodes, which you label with the compute.yaook.cloud hypervisor label. And how does this look like? So just for reference, this graph again. You can query this in Kubernetes via labels that the operator sets. And just as an example, what stateful sets and pods are created from the neutron OVN agent resources, it's looking like that. So basically, you can see that you have stateful sets for controller, for the OVSDB servers, for the local ones, and for the vSwitch daemons. And you also got one for the metadata agent. So if you now wonder why only one metadata agent and all the other things have two, this is because the test cluster that I am showing here, it has one gateway node and has one compute node, and only the compute node gets the metadata agent. The metadata agent is responsible for providing this endpoint to VMs where they can query cloud init data, where they can query their instance ID and so on, which is mapped with a link local address into the address space of the VM. So how are the resources mapped from OpenStack to OVN? So first of all, there's a thing called the controller agent and controller gateway agent, so which you can query via the OpenStack API. This is provided by the OVN controller binary. And then you have things like network. So these are just the most important abstractions that we need to consider. Network translate to a logical switch in OVN, a router to a logical router. Ports, depending on where they belong to, are logical switch ports or logical router ports. Security group rules also map to something that's called access control lists in OVN. I took subnet here. It's not a perfect mapping, but you can find parts of that in the DHCP options table in OVN. So let's have a look at an example. Just wanted to show this at the end of my presentation. All this theory is a little bit boring maybe. So I thought I have a little shell session. So I recorded this and made this a little bit pretty so we can follow along. I thought let's start empty with my little test cluster. Let's have a look at the network agents here. So it's a very simple test cluster, basically what I mentioned before. It just has one gateway node and one compute node. And if I query the network agent list, you can see that I have a controller gateway agent running on the gateway host. And I have on the compute nodes, I have the metadata agent and just an ordinary OVN controller agent. I started empty, so there is no network. I have no server running, no instance running. And now the first thing is, if I create the northbound database now, which has a handy shortcut command, which is just OVN -nbctl show. By the way, in Yaook, I need to go into a specific pod to be able to run this command because everything is like in its own pod running. So we have different stateful sets for the northbound and for the southbound database and so on. And you can see it's empty at the moment because also my OpenStack Neutron database is basically empty. But the southbound database has already some entities inside it, mainly the chassis. So it already knows about the gateway and the compute chassis. And it already has the Geneva tunnel configured that's between these two nodes. Which is also what's also important. I just went into the Open vSwitch daemon pod to get the configuration there. So if you use OVS vSCTL, you can query the OVSDB, which is running locally, and the Open vSwitch table contains one single row, which is used for the configuration, and there's a column external IDs. And there OVN puts a lot of things. Most importantly right now are the OVN and OVN bridge mappings and the CMS options. So maybe you remember this. We want to have the gateway node enabled as a chassis. So this is the option that we set here. And we also need to set some bridge mappings so we can go outside if we want and if we create the right network definition for this. So let's start with it. Let's first create the provider network and let's see how things change in the northbound and the southbound. So you've seen this command before. It's just the same. I will just create a network, my provider network of type flat, and it will be mapped to this FysNet, which is in the OVN bridge mappings, which you saw on the last slide. I will create a subnet, and then I will have this listing at the end. And if I now go to the northbound database and query it, you already see that there are some things going on. So it puts some entities in there, a logical switch and 2 logical switch ports. The southbound database at the moment stays the same. Now going to the next, let's create a tenant network. So in the last step, we created a provider network. So for going outside of the Geneva tunnels into something external, the tenant network is the one which is handled by Geneva. And I create again a simple network. I assign a subnet with a subnet range, and the result is this. If I query now the northbound database, you will see that there's another logical switch being created with just a logical switch port and nothing more. Why is that? Yeah, there's nothing special going on at the moment. Also, the southbound database doesn't show anything because there is no physical thing going on. So there is nothing where the port can be actually bound to. There are no ports really which are, for instance, connected to a router or something like that, because we did not create a router. So let's create a tenant router. I will call it just tenant router and attach it to the subnet which I created before. And now things get interesting. If I look at the northbound contents again, I will see that the logical switch for the tenant network changed. It has now a router port connection. So it has another logical switch port, which is connected to the logical router port on the router. And this is also an entity which is new here, the router tenant router with a logical router port. And you also see that it's got assigned the correct network because I assigned the subnet tenant net to it. And next one is the southbound, which still stays the same, but we will change it in a minute. So let's attach a tenant router to the gateway. So my goal is to, in theory, go outside and be able to communicate with the outside world and not just in my tenant network. So what I do is I change the router in OpenStack and set an external gateway. And now also interesting what happens. The logical switch, which is representing the provider network, now gets another port, which is a logical switch port connected to a logical router port on the router, tenant router. And this one now gets an IP address assigned from the subnet that I attached to the provider network. And it also has now a gateway. So this is because this is an external gateway. And as I've shown you before, these routers, they are like distributed and they reside on specific gateways. And this just shows on which gateway chassis this router is currently residing. And because I only have one in my case, it just shows one. And another important thing to note here is we get a NAT entry, so a network address translation entry, which is basically the entity to specify what happens if some port on the tenant network is communicating to the outside. It will get its network address translated to the external IP of the router, of the tenant router. And yeah, that's the rule that OVN creates for us in this case. Now, in this case, also the southbound database changes because OVN now sees, okay, I need to update the port binding. And because the logical router port is residing on the gateway. So this basically corresponds to this line here, right? And the last step that I wanted to show to you, which is also interesting to see, let's just create a simple demo VM with a service image and see what happens there. So this is very simple. It will just on the network that we have created, because we specify this here, tenant network, it will pick the corresponding logical switch and create a logical switch port there. And this is basically the thing that we see in the northbound DB, but also the southbound database changes. There will be another port binding because on the compute node now we have this port residing. And that's it with my example. I just wanted to share a little bit of insight on logical flows, which was one of the, oh yes, Ariane? Sorry.
I can give you maybe like 2 or 3 minutes if that's fine.
Oh, I'm over time. Okay, I just wanted to show a little example of a logical flow. Maybe you have seen here this little port, a local port that we have here, which has address 0.2. This is the DHCP port that we have. And in OVN, everything is emulated by logical flows, and even the DHCP response is programmed with logical flow. This is just one example that I wanted to show here. It corresponds to the example that we just created. And with this, I will finish my talk. Sorry for overshooting this. And now I'm open for questions and answers. And thank you very much for listening.
Perfect. Thank you so much, Martin. There has been a discussion in the chat while you were presenting that was on, Bruno was asking how are those node role labels set, and Jan-Philipp already answered that it's up to the operator. But maybe is there something that you would like to add to this?
No, that's right. So you can, of course, add some automation with that. So maybe you're running a netbox somewhere, then you could drive this whole stuff via a netbox maybe. But in theory, you just set it manually.
Mm-hmm. Are there other questions or comments? You can either write in the chat or just speak up, whichever feels comfortable. There is another question in the chat. Where is the connection tracking happening? So does the NAT table fail over when the gateway node disappears?
So this is actually happening at the kernel level. And as far as I know, this is not synced when you fail over.
Perfect. There was also some nice feedback on your presentation. So also this should be mentioned too.
Yeah, thank you.
Is there anything else, any questions? If not, I am sure that people can approach you anytime and after the talk. Then I will...
Feel free to reach out, yeah. There is a Yaook IRC where you can reach me, but also a lot of other persons developing Yaook. I heard that we also have a Yaook mailing list, but there's also an OVN or OVS mailing list, which you can use. So feel free to reach out. And my email address, I can quickly put it into the chat here if you have some more questions. It's this one.
Perfect, yeah.
So I forgot to put this on the slides. Sorry.
All good. Yeah, I just added the Yaook meeting link. I hope this is the correct one and it works, but yeah.
Yes, thanks.
Nice. All right, then I will see if I can now share my presentation again. Yes, it does work. There is some typing going on in the chat, but we will see what's happening there. In the meantime, let's jump over to some news and events. Oh, Helena just dropped the Yaook mailing list. That's very nice too. Thank you. And then, yeah, news and events. First of all, it's still November, so it's still the ALASCA Summit month. So I think Helena can say a few words to sum this up.
Hi, everyone. Yeah, just a really quick recap on this. Well, not really a recap, more so a thank you, because I think most of the coffee machine, sorry. Most of the people in this chat have already have been to the summit. So you know what was happening there. But we just want to say a huge thank you to everybody again for just being there, for participating with talks and with workshops, or of course through sponsoring. It was a really great event again, and we are already involved in planning the next one. And yeah, it was great. If you have any further feedback, you can always let us know. I do want to also let everybody know that we did record the talks, because people have asked about this. We did record those. It's just taking us a little bit of time to cut them and get them ready for publishing, because that's a lot of footage. But we are excited to provide that service for the community. So if you weren't able to make it, or you want to rewatch one of your favorite talk, or your own talk if you dare, we'll let everybody know when those are published. Yes. So thanks so much.
Perfect. Thank you, Helena. And then there's one more thing that we would like to announce, and that is that more projects, open source projects, have joined ALASCA. Maybe you've heard it before. I think we've already announced it at the summit too, and it's been in our recent community digest, but still in the tech talks, I think it's a nice opportunity to mention this as well. So on the one hand, we have ACU, which is a standardized platform for efficient monitoring of hybrid cloud infrastructures. This is was being started by D-Nation, and they decided that moving it to ALASCA would be a good idea, and we are really excited about this. The logo is still in progress, but once it's finalized, you will definitely get to see it. And then we have another project too, which doesn't have a logo and a name yet, but as far as I know, there is work going on in the background. But it's a separation control layer that was started by the Secunet and is now being also developed by the D3TN and Cypress Technology. So all of those are also ALASCA members. And it's a minimal infrastructure management solution with a security-focused architecture. So this is really, really nice for us to see how also our technology stack is evolving, and that projects have the trust in us that ALASCA is a nice home for them. Yeah, which we are really happy about. This is the news and events from our side. Is there anything else that you would like to add? Something I forgot? Something that's interesting? I don't see anything being mentioned. Well, then I would like to just repeat the call for speakers for 2026. We are working on a nice lineup for you and have some interesting topics already. But if you have something you want to present, or also if you have an idea and be like, well, I wish, I don't know, this technology would be presented, then maybe we can approach them too and ask them for a talk. So always, yeah, get in touch with us, and then we can figure this out. And with this, we are at the end of today's Tech Talk. The only thing I have left to say is, well, join us again if you want to next year. The first Tech Talk of 2026 is on January 30th with Matthias Büchse. Matthias is the project manager of Focus, which is ALASCA's funding project, and he will show us how to build an SCS-compliant cloud environment for the benefit of the ALASCA community, which I think is a nice way to kick off the new Tech Talk year. It's the end of November, not much left of this year, and I guess in the name of the whole ALASCA team, first of all, thank you to all the speakers that we've had this year. Thank you, Martin, to you for closing this season. It was a very nice time. We wish you a very joyful Christmas time, nice holidays, even if it's still a minute until we're there, and then a smooth ride into the next year. Thank you for being here today, and we will see you next time. Bye, everyone.